Okay, so for today, what we're going to be getting into for this lesson is a little bit of some airflow and oil heat calculations. In previous lessons, we have already discussed efficiency, combustion, and really all of the components that are associated with at least an oil heat piece of equipment. So now what we're doing is now we're going to start tying everything together to fully understand the importance of checking and making sure that a piece of equipment is actually working at its highest efficiency. It's not always going to be just how the furnace is burning a fuel oil or a fuel gas. It's the overall operation of that unit that plays a part in how a piece of equipment is actually working. And that is obviously airflow and understanding our oil heat calculations and making sure that we are not overfiring or underfiring a unit. So airflow and the components that are in a unit that is used to create it, and that's going to be our fans, our motors, and obviously our ductwork, they're designed to move heated or cooled air through a conditioned space throughout the building and return it to the unit so that it can be conditioned again and then redistributed throughout the space. There's a lot of factors that can affect, airflow in a unit. It could be positively affected, it could be poorly affected, or so we have to look at the ductwork. We got to look at our blowers to make sure that obviously that they're clean. We got to make sure that they're in the right direction, they're flowing in the right direction, not flowing backwards, or the blower wheel is actually installed backwards, which I've seen. It could be by mistake, it could be by just someone that just didn't understand how something was to work. But all that stuff is going to affect how a system's performance is, its efficiency, whether or not it's going to be reliable for the operation. Some of the areas that kind of affect the air distribution of a system is making sure that you are supplying the right amount of air to your conditioned space. So in other words, if you're in a home, at least the minimum thing that you can do is go around and make sure that all the supply registers are actually open and not blocked. Make sure the return air vents are the same thing. They're not blocked or vent or shut off for some reason. To supply the air to each space so that the air motion is adequate and not drafty. So a lot of times what that's going to be is maybe the fan is operating at a too high of an RPM. So a person might actually complain that they're feeling like a cold draft on them. Sometimes what has to happen is you got to maybe take the blower and actually lower the fan speed down maybe a notch to try to eliminate something like that, because the air is just happily moving too fast. You're conditioning the air to maintain proper comfort. Well, obviously that's all a part of making sure that the burner is firing at the correct BTUs and clean air filters and checking everything. Your return air for all your conditioned space, that just comes down to ductwork design. Is the return air ductwork adequately sized to move the correct amount of air through the air handler and all that stuff? Operate efficiently without excess power consumption or noise. Well, that's just simply looking at the unit and making sure that everything is the way it's supposed to be. Okay, operate with minimum maintenance. Usually if a furnace is all well tuned up and working correctly, You know, it should be once a year, at least, for maintenance. If it's not, you're going to have callbacks. You're going to have service calls. You're going to be going back constantly and repairing units that, to be quite frank, were never actually tuned up to begin with. Okay, most air distribution systems are forced air systems, and that is the primary components of those is obviously going to be a furnace or an air handler of some sort. An air distribution system, that's going to make up of your supply and your return air duct. It's going to be of your grills, registers that allow the circulated air to enter the conditioned space and return it to the heating or cooling system so that we can honestly raise or lower the temperature depending on what we are actually trying to do with this unit. In modern air systems, air moves through the ductwork because the fan creates a pressure difference in the airstream. You know, lower pressure is in the return. Your higher pressure is going to be in your supply. The amount of air the blower can move and the amount of energy needed to move the air is controlled by the resistance to your airflow from the ductwork and all the components in the airstream. Now, that could be a bunch of things. That could be an air filter. It could be 90-degree elbows in the ductwork. It's going to be your dampers, zone controls, all those things that are associated with the movement of the air is going to play a factor in how much energy and how much the blower can actually move. Like, for example, if you have a oil-fired furnace with a coil, evaporator coil on top of it, that's a restriction. Now the blower has to move the air not only through a heat exchanger, but it has to also move the air through an evaporator for air conditioning. That takes energy. So CFMs is important to make sure that we have the correct amount of airflow through that unit so that we can condition a space efficiently. Okay, the capacity of the fan decreases when it has to move air against a pressure difference. That pressure difference is created when air is constrained by the ductwork. We have three different types of pressures that exist in our ductwork. And that's going to be our static pressure, our velocity pressure, and the total pressure of the entire system. Now, when we think about static pressure, think about it like in a balloon, okay? The definition of static is lacking in movement or change. So when a balloon is blown up, the air within pushes out evenly in all directions, creating static pressure inside the balloon, causing it to expand. Okay? The air that makes up the Earth's atmosphere has weight. It pushes down on the surface at about 14.7 pounds per square inch at sea level. So, this is called atmospheric or quote-unquote barometric pressure. The static pressure inside an inflated balloon is pushing against atmospheric pressure outside the balloon. Okay? So if the static pressure is greater than the atmospheric pressure, the balloon is going to inflate. So now let's take that and let's use that in terms of a blower inside a furnace. When the fan blows air into the ductwork, it creates static pressure. Okay, that's going to be on the inside interior surface of the ductwork. So the ductwork is pressurized, just like a balloon. Okay, so static pressure in the duct pushes in all directions inside the ductwork. High static pressure is going to lead to lower airflow. It's static pressure is what's going to help move air down the ductwork so that we can get the air from the blower all the way down to the very end of that trunk line of ductwork. Velocity pressure simply just means speed, how fast the air is moving. High pressure air always travels towards lower pressure. Okay, so remember, in our supply ducts, we have positive pressure coming out. It's forced coming out of our supply ducts. Our return is more like a negative pressure or a lower pressure. It's that pressure difference between static pressure and velocity pressure is what helps move the air through a furnace or air handler. Velocity pressure determines the speed of air through the ductwork. Okay, the pressure coming out of the end of a balloon, like when you open up a balloon and you just let the air out, right? That's all velocity. So think about when you have all that static pressure sitting inside the balloon and you let it go. Think about it. That's like a blower. The blower has now turned on. It has now created a pressure difference. Total pressure is the sum of the static and the velocity pressure inside your duct system. Okay, it is the pressure produced by your fan or your blower. Okay, so due to the pressure inside a ductwork system, we can use a couple different tools to measure what our pressures are. And that's going to be, we can use an inclined manometer, we can use a digital manometer, or a magnehelic type of tool to measure your duct static velocity and total pressure, and those are going to be measured in inches of water column. Okay? Because the readings are so low, usually less than 0.025 pounds per square inch, we have to measure in inches of water column. Okay, 1 inch of water column is the height in inches the pressure will lift a column of water. Okay, 27.7 inches of water column is going to be equal to 1 psi. So here we have our tools. We can use a manometer, we can use an inclined manometer, or a magnehelic to measure our duct pressures. For every 1 pound per square inch of pressure, a column of water will rise to the height of 27.68 inches, or 2.3 feet. In special low pressure applications, such as when we do blower door testing, if you would ever want to get certified in that, that's actually a very good tool to also have on in your tool belt. Is dealing with blower door testing to see about home efficiency. We measure those in pascals. Okay, normal pressure at sea level is 101.3 kilopascals, or usually rounded to 100 kilopascals. Now, when we're thinking about this in oil heat and we're doing an efficiency test, we have to take our draft readings, and one of those readings is over the fire. So if we were kind of using this as a reference, we could think of a typical over the fire draft, which is negative 0.02 inches of water column. That's going to equal to about 5 pascals. When it comes to our fans and our blowers, the fan and blower is what provides that pressure difference necessary to force the air into the supply duct through the grills and registers and then into the conditioned space. Okay, so the blower has to, again, overcome a lot of resistance of any component in the airflow. And again, that could be our air filters. Okay, air filters create a resistance, especially if they start getting plugged up. Your evaporator coils, again, they're going to create a lot of resistance. They're going to create more resistance, especially if they're dirty. Your heat exchangers, your dampers, as well as the pressure lost involved in the return of air through the return air duct. So when you think about it, a blower really has to do a lot of work to get a furnace, air handler, whatever the hell it is that we're working on, to operate efficiently. And it's like I always say to a lot of my students is, well, if one of the dominoes happens to fall, the rest of them are going to fall. You're going to have a problem. Okay? And it's just like when we're dealing with the combustion triangle. You got to have air, fuel, and spark, or a heat source, to get something to burn. If one of those is missing or not correct, it's not going to light. The same thing applies when it comes to dealing with airflow in a unit. It plays a factor in a unit's efficiency. We have to make sure that these things are correct. If not, something's going to go wrong. So when we think about the terms of fan and blower, well, those terms, honestly, in this field are used interchangeably. Okay, the term blower is described in applications where the device must work against the resistance of a duct system, such as a forced air system. And then the word fan is described in applications where high quantities of air are needed with little resistance to airflow, such as a condenser fan motor when we're dealing with an air conditioner. Okay? The two types of blowers that are commonly used in heating and cooling is going to be our belt and direct drive. The belt-driven blowers, which are commonly found in a lot of our older air handlers, they're going to have a blower motor mounted outside the blower housing and are connected to the blower wheel by pulleys and a belt. So in order to adjust anything on these, the blower speed is adjusted manually by a change or adjustment of the pulleys. So increasing the size of the motor pulley is going to increase the RPMs of the blower. Increasing the size of the blower pulley is going to decrease the RPMs of the blower. So for example here, to calculate the fan RPMs with a motor RPMs of 1725, it has a 3-inch diameter motor pulley and a 7-inch diameter fan pulley. To do that, we are going to use the following formula. We're going to take the diameter of the motor pulley and divide it by the diameter of the fan pulley, and then we're going to multiply it by the motor RPMs. Okay, so we know that we have a 3-inch diameter motor pulley and a 7-inch diameter fan pulley. So we're going to take those two numbers and we're going to divide them together. 3 divided by 7. And then we're going to multiply it by the RPMs of the motor, which we know is 1725. So we plug in those numbers. 3 divided by 7 is going to give me 0.4286. And we're going to multiply that by 1725. So 0.4286 times 1725 is going to give in 39 RPMs. That would be the calculated RPMs that we would need to make sure that our motor is running at. Direct drive pulleys, they're going to have a blower wheel mounted directly to the motor shaft. The blower speed is adjusted electrically by changing the blower motor terminals or changing the settings of the blower speed selection switches on the motor's related circuit board. Okay, in most residential equipment, you're going to have especially in more modern up-to-date equipment, you're going to have most likely multi-speed direct drive motors. Okay, next that we're going to have to think about, and it's honestly kind of not really taught so much in technical schools, is fan laws. Fan laws really kind of help a mechanic in understanding relationship between, you know, the blower that they're working on and airflow. Because what it does, it describes the relationship between a couple of things. It describes the difference between, obviously, like it says, your cubic feet per minute, or CFMs, revolutions per minute, which is your RPMs, your static pressure, and horsepower. Those fan laws gives us, and it makes us understand that what we do to a fan is going to affect airflow performance. So if a fan isn't operating at a correct RPMs, it's going to affect its ability to give us the correct amount of CFMs. It's going to affect the static pressure inside the ductwork. It's going to affect the horsepower of that motor. So again, it's back to like I said before. If a unit fan isn't operating correctly, it's going to affect other areas of that unit's performance. So if a furnace isn't getting enough CFMs across the heat exchanger, I run the risk of overheating my heat exchanger, maybe possibly hitting a high limit switch because I'm just not moving enough air, right? Or if it's going too fast, I'm cooling the air off too quickly and I'm not going to achieve my correct temperature difference, which means the furnace is going to run longer. That affects efficiency, no? Of course it does. So we need to understand all of these components to make sure that something is working correctly. A fan's performance varies depending upon the condition under which it operates. That's a big thing. One furnace or one blower, it can move 400 CFMs in this unit based off of its design and ductwork. But if I put that very same unit or that very same blower in a different unit that has a different type of configuration in ductwork, it may not be moving 400 CFMs. It might move 300. The amount of air a fan moves, the speed of the fan, and the motor horsepower are all directly related to each other. This can be proven by our fan laws. Okay, fan law number 1 states that the amount of air delivered by a fan varies directly with the speed of the fan. Okay, and we can prove that mathematically by using either one of our given formulas here. Okay, formula number 1 is our new CFM equal to our new RPMs times the existing CFMs divided by your existing RPM. Or you can use the formula new RPM equals new CFMs times existing RPMs divided by the existing CFM. Okay, and I'll go over this in a little bit, but let's just get through the fan laws. Fan law number 2 states that static pressure or resistance of the system varies directly with the square of the ratio of your fan speeds. Okay? And we can prove that by using the mathematical formula. New static pressure equals your existing static pressure times the new RPMs divided by the existing RPMs squared. Fan law number 3 states that the horsepower varies directly with the cube of the ratio of the fan speeds, or simply using the formula existing horsepower times the new RPMs divided by your existing RPMs is going to give you your new horsepower. Okay? So for example, using those 3 fan laws that I just went over, assuming an existing system has the following conditions. Okay, we're moving about 1,000 CFMs. The motor is at 825 RPMs, and we have a static pressure of 0.5 inches of water column with a fan horsepower of only a third. Okay, with an increase of airflow to 1,200 CFMs. Oh, so we raised the CFMs in this guy. So what's the new RPMs, what's the new static pressure, and what's the new horsepower that we need to have in order for this unit to work? So if we use fan law number 1, which states that the amount of air delivered by a fan varies directly with the speed of the fan, we can plug in our numbers. We know that we have to have 1,200 CFMs, and we're dealing with 825 RPMs. So 1,200 times 825 gives us 990,000. Okay, we're going to divide that by 1,000 because that is our current CFMs, right? So if I take 990,000 divided by 1,000, my new RPMs needs to be 990 RPMs off of that motor. If I wanted to calculate the static pressure of what I needed now, we know that we were dealing with 0.5 inches of water column for this unit. So I have to plug in my numbers. Okay, so 0.5 times 990 divided by 825 squared, that's going to give us 1.5 times 1.44. And if I multiply those together, my new static pressure is now going to be 0.72 inches of water column. So my static pressure inside my ductwork is going to now have to be at that measurement in order for me to be moving the air and keeping the static pressure up inside the ductwork. To calculate my horsepower, 0.33 times 990 divided by 825 cubed is going to give me 0.33 times 1.728. And now my new horsepower is 0.57. So you can see by taking these mathematical formulas, what I do to a blower or what I do to a ductwork is going to adversely affect the airflow performance of that unit. I can either raise it or I can lower it, depending on what I do to my fan speed, what I do to my ductwork, whether I'm adding a zone or extending ductwork or removing ductwork or whatever the heck it is that has to happen. You are going to adversely affect that performance of those components. So now when it comes to oil heat calculations, we have to make sure that not only are we using the correct amount of air across the heat exchanger and then down in our ductwork, we got to make sure that our nozzles are the correct size, that we're not overfiring or underfiring a unit. So we have to make sure that we are putting in the correct nozzle that is capable of giving us the correct amount of BTUs to heat a space. So to determine how much heat a nozzle is capable of, we have to multiply the GPH of the nozzle times 140,000. We know that number 2 fuel oil, 1 gallon of number 2 fuel oil, is going to give us 140,000 BTUs. So for example, a 0.75 gallon per hour nozzle at 140,000 BTUs is going to put out 105,000 BTUs of heat. A 0.5 gallon per hour nozzle is going to put out 140,000. That's going to only put out 70,000 BTUs of heat. Now, that's all fine and good. But those numbers are only correct if that oil-fired piece of equipment is running at 100% efficient. Which we all know oil heat is not 100% efficient. It is probably more somewhere around 80-85% efficient. Maybe as high as 90. So those numbers are only correct if I'm 100% efficient. Okay? And those numbers are only correct if our pump pressure is set at 100 psi. Which we know that some of our newer, up-to-date burners are not operating at 100 psi. They're operating at about 140, 150 psi. So those numbers are different. Using a furnace efficiency percentage, though, and an accurate BTU output can be calculated, okay? So, if we have a furnace and we have a 0.5 gallon per hour nozzle in there and we did an efficiency test and we determined that it's about 80% efficient, okay? Which means 20% of the heat that this furnace is now generating is going out the chimney, 70,000 BTUs lower, okay? So to calculate this, to figure out exactly how much BTU output we are actually dealing with, we got to plug in our numbers. Okay? So 0.5 gallon per hour times 140,000 BTUs, that's going to give us 70,000 BTUs. So at 70,000 BTUs, we know that it's only 80% efficient. That's only giving us 56,000 BTUs of actual usable heat off of this unit. Okay? So which means about 14,000 BTUs of heat is going out the chimney, which comes out to about 20% of that 70,000 BTUs that we originally came up with, right? So the importance of checking what your output rating is on your furnace, and oh, by the way, a lot of that stuff is found on nameplates of your furnace. You can determine whether or not you are achieving the highest amount of BTUs per dollar that a furnace is operating at. Compare apples to oranges. What does my nameplate rating say? What is my actual calculated BTU output reading is? Make the necessary adjustments. When it comes to calculating airflow, along with our nozzle sizes, we have to understand that air is calculated in cubic feet per minute, right? It's volume. Okay? To calculate the CFMs of a furnace, the BTUs has to be known. We got to know that. Okay? So Q is the quantity of usable BTUs of a system. What's actually being put into the conditioned space. Okay, so again, we have a furnace here that has a 0.5 gallon per hour nozzle, and it's 90% efficient. Wow, it's running really damn good. So let's plug in our numbers. 140,000 times our nozzle size, 0.50, times its efficiency, 0.90. We need approximately 63,000 CFMs of air to be moving across this furnace to help achieve what we are reading. Okay? Once we achieve and we figure out how many CFMs we need to move across our heat exchanger, our combustion chamber, we have to take a couple of readings. The first thing that we're going to be taking is the supply duct temperature. Okay, we're going to take that temperature after the furnace has been running for probably about a good 5-10 minutes with the burner and fans on. Then you are going to take another temperature reading. That temperature reading is going to be at the return. Okay, you're going to take a reading at the supply. You're going to take a reading at the return, both with the burner and fans on. You are going to subtract those two readings from each other. Subtract the supply air reading from your return air reading. And that's going to give you your delta T, or your temperature difference. Okay? Then you are going to multiply that number by 1.08. That 1.08 is a constant. So the formula is as you see here. Okay? Q divided by your delta T, your temperature difference, times 1.08. And that will give you your CFMs. Okay, so let's plug those numbers in. We know that we are dealing with 63,000 for our quantity, right? Our CFM, 63,000. We take that number and we divide it by our delta T. We had a delta T, say for example we had 145 degrees supply and we had a 69 degree return. 145 minus 69 times 1.08. So here we are. We have 63,000 divided by 76. Okay, 145 minus 69 is going to give you 76 times 1.08. 76 times 1.08 is going to give you 82.08. So 63,000 divided by 82.08, you need 767 CFMs of air.